Hello. I hope you've enjoyed our lectures so far on the development of the trigonometric functions. Today we'll spend some time studying the sine and cosine functions, and in fact we'll look at their graphs. You'll recall we defined the 6 trigonometric functions 2 ways. First using a right triangle, and then we defined it for an arbitrary angle, positive or negative. And we noticed near the end of the previous lecture that you can think of the sine and cosine function as functions of a real variable. For any angle theta, you can compute sine theta and cosine theta. So I'd like to explore that functional relationship of the sine and cosine function a bit deeper. But before we do, let's recall that definition of the trigonometric functions, that definition using for an arbitrary angle. Here's how it goes. You let theta be an angle in standard position, and let xy be the coordinates of the terminal side of that angle. And of course, r is the distance from that point back to the origin, and we assume it's non-zero. And then sine was defined to be y over r, and cosine was x over r. And the other 4 trigonometric functions were also defined, but today I'm going to focus on sine and cosine. Here's a picture of what we're talking about. xy is the terminal point, r is the distance to the origin, sine is y over r, cosine is x over r. Okay, now let's go a little deeper. For every angle theta, you can compute sine of theta and cosine of theta. So these are functions of a real variable. The input is a real number, theta, the angle. But now we're going to change the letters on you. Instead of using theta to represent the angle, we're going to use the variable x. This is not the x of the ordered pair xy that I just alluded to a few seconds ago. Ignore that for the moment. Just think of x as being the angle. Okay, we're just relabeling. Instead of using theta, we're using x. And the output, sine x, we'll call y, or f of x. And we have a function, f of x equals sine x. You give me x, you give me an angle, I will compute y, the sine of that angle. What's the domain of our new function? All real numbers. What's its range? Well, remember that the sine and the cosine are sandwiched between -1 and 1. So the range is not all real numbers. It's a small closed interval, -1 to 1. And also recall that periodicity. The sine function and the cosine function is periodic with period 2 pi. By that I mean sine of x plus 2 pi is equal to sine of x. Because if you're at some angle x and you go all the way around 2 pi radians or 360 degrees, you're back to where you started from, so the sine value will be the same. All right. What does the graph of the sine function look like? Maybe you've seen a picture of it before. It's a good-looking graph. You'll like this graph. And how could we do it? Well, here's how your graphing calculator would do it, or here's how you would do it if you had a lot of time. You would pick x values. You would pick certain angles and compute the sine of those angles. And you would do like 1,000,000 of them and start connecting the dots. Just like we point plotted back in earlier lectures with the exponential function. For instance, you could let x be 0 and sine of 0 is 0. So the point 0, 0, the origin, is on the graph of the sine function. You could let x be pi over 6, the angle pi over 6. Remember what the sine of pi over 6 was? Yeah, 1/2. So you would plot that point, pi over 6, comma, 1/2. How about pi over 4? Oh yeah, sine of pi over 4 was square root of 2 over 2. So you would plot that point. And then you would plot, say, sine of pi over 2. And remember that that's equal to 1. And you would plot more and more points. Here I've indicated on the graph a few of those key points. And then you connect them with a smooth curve, and you get this very nice sinusoidal behavior, this periodic behavior. You see how it goes up and down, up and down. Here are some important features of this graph. Please savor it. When you're having breakfast one day, bring the graph and put it next to you and start looking at it. For instance, it crosses the x-axis at 0, pi, 2 pi, minus 2 pi. Those are the x-intercepts. How high does it go? It goes up to 1, and then it goes down to -1. Notice how it repeats itself. At 0, 0, it's at the origin, and then over at 2 pi, it's back at 0 again, and you've had a complete period, a complete cycle of the sine curve. And then that cycle is repeated over and over again. Again, the domain is all real numbers. This graph goes on forever in both directions, but the range is -1 to 1. Notice also it was an odd function, wasn't it? Look at the graph again. It's an odd function. It's symmetric about the origin. We've talked about the intercepts. Where does the maximum value occur? Well, at pi over 2, because sine of pi over 2 is 1, and then by periodicity, 5 pi over 2. That's pi over 2 plus 2 pi, etc. So there are lots of high points, and there are corresponding low points. Say at 3 pi over 2, the value is -1. Okay, so it's a nice graph. It's got interesting features. What's the cosine graph look like? Well, the cosine graph is very similar to the sine graph. Here's one of the big differences. Remember that sine of 0 was 0? But what's cosine 0? Oh yeah, cosine 0. I look back at that table. Cosine 0 is 1. So when x is 0, y is 1. So the cosine hits its maximum value right away when x is 0. And then it still has this periodic behavior. In fact, the cosine graph looks just like the sine graph, but it's been shifted, hasn't it? It's been moved. They are translations of each other. You can check that on your graphing calculator. Try this experiment sometime. Graph y equals cosine x, and also graph y equals sine of the quantity x plus pi over 2 being the shift factor here. You'll get the same graph. They'll be on top of each other. In fact, you won't notice any difference. You'll graph it and you'll think you've only graphed one function. Okay, so the cosine graph is very similar to the sine graph. It's now an even function though, isn't it? Notice the symmetry across the y-axis. It's an even function, not an odd function, but it has the same domain and range of the sine function. Domain, all real numbers. Range, -1 to 1. Okay, let me make some comments about the sine function and the cosine function. These are periodic functions, period 2 pi. They repeat themselves, one cycle every 2 pi. So they're used all over science and engineering to model periodic behavior, such as waves, the tides, heartbeats, movement of pendulums, clocks. We saw harmonic motion with a spring last lecture. All these kinds of engineering applications require knowledge of trigonometric functions. Needless to say, again, this course is called Pre-Calculus. Trigonometry plays a key role in all of calculus. When I teach calculus, I'm using trig functions every day. And students need to be pretty sharp with some of the trig values and the shapes of trigonometric curves in order to be successful in calculus. And I'll admit to you, I think graphing trigonometric functions can be difficult. Of course, graphing sine and cosine, we just did it. That's not so bad. But now we're going to massage them. We're going to complicate things. We're going to look at some trigonometric functions based on sine and cosine, but with some tweaking. And you'll see that, as we say, it's more interesting. Remember, that's what mathematicians like to say when they really mean it's more difficult. Let me start with a fairly easy example. What does 2 sine x look like? F of x equals 2 sine x. What do you think now? Well, I know what sine x looks like. Here, I'll draw it for you, like this. Well, what about 2 sine x? Well, the only difference here is when x is pi over 2, sine of pi over 2 used to be 1, and now it'll be 2, 2 times 1. So all we're doing is changing what we call the amplitude of the curve. Instead of going between -1 and 1, it will now go between -2 and 2. So let's graph it on, say, the interval -4 to 4 pi. Here's what the picture would look like. And this is a nice graph, I think, because we have, first of all, in green, the sine function, our old friend, the sine function. You see it there, starts at the origin, and at pi it's 0 again, and at 2 pi it's 0. And it goes up to 1 at pi over 2. That's the peak. Well, 2 sine x is stretched. It goes from 0 up to 2 when x is pi over 2. We've changed the amplitude of the function. Okay, so that wasn't so bad. Putting a constant out in front didn't upset us too much. But now I'd like to look at sort of a whole class of functions. I want to talk about what we call the general sine and cosine curves. And these are curves of the following form. Y equals d plus a sine quantity bx minus c, and the corresponding cosine equation, y equals d plus a cosine bx minus c. There are 4 constants here, and depending on your application, those constants can be determined or be given to you, and those constants will change the shape of the sine curve. It'll always have the basic shape, up, down, but it might be going up higher, it might be shifted, it might be moved vertically, etc. So let's explore these complicated equations, and I'm going to do it by focusing on each constant in turn. All right. What about what we call the amplitude? We just did an example with amplitude. 2 sine x had amplitude 2. That's affected by the value of a. And technically speaking, the amplitude represents half the distance between the minimum value and the maximum value. Remember that problem 2 sine x went from -2 up to 2. So half of that is 2. The whole distance is 4. So the amplitude there was 2, and in general, the amplitude is the absolute value of a. If a is positive, then it's just a. That's the amplitude. Let me show you a picture of this situation. Let's graph 1/2 cosine x and 3 cosine x in the same Cartesian coordinate system. Okay, this is pretty easy, actually. This part's pretty easy, I think. Here you see 3 graphs, actually. One graph in blue is our old friend cosine. Okay, cosine goes up to 1. Notice that at 0, 1, it touches there. And then we had the function 1/2 cosine x. Well, that will change the amplitude. It'll squish it down a little bit, and that's drawn in green. It has the same general shape, it just doesn't go as high. And then we have 3 cosine x, and that has a much bigger amplitude. The amplitude is now 3. So it's a big wave. It's like there's a storm and the wave has gotten quite big. So you see how these are related to each other, and I hope you sort of say to yourselves, oh, amplitude's pretty easy. Let's go on to looking at the cycle, the period of these trigonometric functions. This is slightly more interesting. Okay, here's how you can analyze it. Sine x completes one cycle. Its period is from 0 to 2 pi, and then it's back to where it started from. So it follows that sine of bx, where b is some constant, completes one cycle from 0 to 2 pi over b. Now, how did we get that 2 pi over b? Well, if x is 2 pi over b, then bx is 2 pi, and sine of 2 pi is 0. So we're back to where we started from. So here's the definition. Let b be, sorry about that, let b be a positive real number. The period of a sine bx and a cosine bx is given by 2 pi over b. 2 pi over b. In particular, if b is 1, the period is just 2 pi, as before. Let's do an example of this. And again, you'll see this is pretty straightforward. What does sine of x over 2 look like? Well, again, you should expect it to look like the sine function. It's got the same amplitude, doesn't it? Amplitude is still 1 here. I don't have anything in front. But I've got the x over 2 there. That will change the period. And b here is equal to 1/2. It's x over 2, so b is 1/2. And hence the period is 2 pi over b, or 2 pi divided by 1/2, or 4 pi. So the period of this function is actually bigger. It's 4 pi. And you can sort of check this. When does this function touch the x-axis? What are its intercepts? Well, 0. Sine of 0 over 2 is 0. And the next time it touches is 2 pi, because sine of 2 pi over 2 is sine of pi. And then at 4 pi, it's completed a full cycle. Here's a picture of both sine x and sine x over 2. And you can see what happens. The yellow graph is sine x. It's our old friend. It starts at the origin, goes to pi, and then back to 2 pi, and then it starts repeating. The green graph is sort of stretched out. The period is now 4 pi. So it completes a full cycle in 4 pi rather than 2 pi. The period is 4 pi. All right, good going. I think we're getting there. We've analyzed 2 of the variables, the amplitude and the period. Now we'll turn to what I think is the most difficult part of this general equation, and that's, what does c do? What's that bx minus c going to cause? All right, this turns out to create translations of the sine curve. It moves it up and down the x-axis. Let's see how that works. It's a little complicated, I admit, but I think you'll find it understandable. Let's first look at sine bx and compare it to sine of the quantity bx minus c. So these are the 2 characters. Sine bx, which I think we're comfortable with, and then sine bx minus c has got that minus c in there. How do they compare? Well, the first guy, sine bx, completes one cycle when bx is 0 to bx being 2 pi. From 0 to 2 pi is a full cycle. So when bx is 0, that means x is 0. And when bx is 2 pi, that means x is 2 pi over b. And we knew that. That was the period of this modified function. What about the second guy? Sine of bx minus c. Well, let's do the same analysis. It starts when bx minus c is 0, because sine of 0 is 0. And it finishes when bx minus c is 2 pi. So solve those equations for x. In the first equation, if bx minus c is 0, x is c over b. Just bring the c to the other side and divide by b. So now x starts at c over b. It used to start at 0, didn't it? But now it's starting at c over b. It's been shifted a little bit. Where does it finish? Well, that'll be at bx minus c equals 2 pi, completing a full period. And now solve for x. It's a little more arithmetic to solve for x here. And you get x equals c over b plus 2 pi over b. I think that makes sense, because watch. If I start at c over b, this new function, I do one period. And remember, the period was 2 pi over b. And that's what we're saying. The finishing value is c over b plus 2 pi over b. Now, I don't necessarily recommend you memorize that. Most people do the following. They solve the equations bx minus c equals 0, and the other equation bx minus c equals 2 pi. But either way gives the same answers. All right, let's do an example. How about the following equation? Y equals 1/2 sine x minus pi over 3. What in the world does that look like? Y equals 1/2 sine x minus pi over 3. What can we say about this? Well, here's a couple of facts about it that we're sort of comfortable with, I think. What's the amplitude? 1/2, no problem. That's the coefficient out in front. So it's not going to be too high. It's going to be squished down a little bit. How about the period? Well, that's the b coefficient. Remember, it's 2 pi over b, but b is 1 here, isn't it? It's just x. So the period is still 2 pi. So I'm comfortable with the amplitude and the period. Now, what about the shift? They sometimes call that a phase shift in engineering. How do we determine that? Well, set the thing inside parentheses, x minus pi over 3 equal to 0, and that implies that x is pi over 3. So that's sort of one of the starting points. And now set it x minus pi over 3 to 2 pi, and you get x equal 7 pi over 3. So from pi over 3 to 7 pi over 3, it completes a full cycle. The period is still 2 pi, but it's been shifted to the right by pi over 3. Here's a picture of both the function sine of, 1/2 sine x, together with the graph of 1/2 sine x minus pi over 3. So we're graphing the two functions together. The graph of 1/2 sine x is a pretty understandable graph. It's basically the sine function squished down so its amplitude is 1/2. Then we've graphed next to it in yellow the graph of our shifted sine curve, 1/2 sine x minus pi over 3. Do you see how it's been shifted? It used to pass through the origin, and now its 0 is at pi over 3. It's just been moved a little bit to the right. Pretty nice, isn't it? So let's sort of summarize some of these graphing ideas for this general curve, a sine bx minus c and a cosine bx minus c. And then we'll go back and attack the final letter d, which will be added. What kind of observations can we make? Well, first of all, if we assume that b is positive, and in most cases it will be, the period is 2 pi over b. Okay, that's good. The amplitude is the absolute value of a. Hopefully a is positive so you don't have to worry about absolute value. And then to get the right hand and left hand endpoints of a full cycle, what do? Well, you solve bx minus c equals 0, sort of the beginning part of a cycle, and then you do bx minus c equals 2 pi for the end of the cycle. Perhaps it wasn't so difficult after all, but no, I have to tell you, it is pretty difficult. I think graphing these shifted sine curves is quite difficult. Plugging in values and checking with a graphing utility sure help. Let's finish off with the final letter. We've done A, B, C, and then we had a D in the front. So now we're going to look at the most general equation possible here, d plus a sine the quantity bx minus c, or with cosine. What does the number d do to this graph? How does d affect the graph? Well, let's think about that. If d were 0, the graph would be just sitting right there. But if d is, say, 5, that means every value gets vertically shifted 5 units upwards. Or if d is minus 3, then everybody goes down 3 units. So d is a vertical translation, a vertical shift of the graph. So we've done a lot of changes with these trig functions, haven't we? We've changed the period, we've changed the amplitude, we've shifted them horizontally, and now we're going to shift them vertically. Wow. You can see how useful they are for modeling because you can play with those coefficients and make the graph look a lot different. Okay, let's do an example, as we always do. What does 2 plus 3 cosine 2x look like? Let's graph 2 plus 3 cosine 2x. What can we say about it? Let's think about it. What are some of the easy things to say? For instance, what's the amplitude? Oh yeah, there's a 3 in front of the cosine, so the amplitude's 3. Okay, I'm okay with that. How about the period? Well, that's 2 pi over b, and b here is 2. So it's 2 pi over 2, or pi. The period used to be 2 pi, and now it's shrunk down to pi. It's going to go faster. Okay, the cycle is shorter now. All right, is there any shift in this curve? No, thank goodness, we don't have a shift. Okay, but we do have a 2 in the front, and that means there'll be a vertical shift 2 units upward. Let me show you a picture of both the curve 3 cosine 2x, which I think we're very comfortable with, and then the shift upwards of 2 plus 3 cosine 2x. So we have 2 plus 3 cosine 2x and the original function 3 cosine 2x. Look what's happened. For the function 3 cosine 2x, it crosses the y-axis at 3. The amplitude is 3. But now it's been shifted upwards 2 units, so the point 0.5 is on the graph. It used to be 0.3. It's been moved upwards 2 units. Let's look also, say, at the low point. The low point used to be at -3, but now it's at -3 plus 2, or -1. And you see I've labeled there pi over 2, comma, -1. That's been moved up from -3 to -1. Wow. All right. Difficult. This is non-trivial mathematics. Let me make some suggestions for graphing techniques. I've pointed this out before, that when you go on and take a calculus course, you spend days, if not weeks, on learning how to graph functions and using some calculus techniques for graphing. But I think we were pretty exhaustive here in analyzing sine and cosine graphs and all the possible shifts, vertical, horizontal, etc. But some advice. It's always a good idea to plot some points. I find point plotting it gives me a lot of confidence when I plug in some points and I start putting them on the paper. And remember, a graphing utility is nothing more than a point plotter. It's just a lot faster than I can do it. Always keep in mind the periodicity. It's really nice to know the period of the function, because then you can repeat it over and over again. You don't have to analyze it too far. Once you know one cycle, it repeats itself. I think you'll agree with me, I hope you agree with me, that the amplitude and the vertical shifts are pretty easy, right? The amplitude is just stretching it, and the vertical shift moves the whole graph upwards or downwards. I think horizontal shifts take a lot more work, don't you? I do. I think those are much tougher. Okay. Let's finish off here with a little application. I've mentioned that trigonometric functions occur in real life. Many things are periodic. Well, here's a great example of periodic behavior. Pulsars. It turns out that the first radio pulsar ever discovered was in 1967 by Jocelyn Bell Burnell, and she was a British astrophysicist. What's really amazing to me is she discovered it as a graduate student. As a young graduate student, she discovers the first pulsar. Pretty impressive. Its designation, it has a name. This designation was originally PSR B1919 plus 21. I'm not sure what that really means, but you can, of course, go to the internet and learn more about this pulsar. What is a pulsar? Well, it's a very small star that is rotating very, very quickly, and it emits beams of electromagnetic radiation. And it pulses. It has a certain period. Boom, boom, boom. Well, Jocelyn Bell Burnell calculated that period to be 1.3373 seconds. Boom, Boom, just like that. And all these pulsars have a period associated with them. And these periods, there are many, many pulsars, they range from 1.4 milliseconds, which is pretty fast, to over 8 seconds. So it's kind of neat that periodic behavior is occurring out there in the sky right now. And to understand it, we need to know some trigonometry. Okay, I hope you've enjoyed today's lecture and yet found it challenging. In the workbook, you'll see some problems where we ask you to try your hand at graphing some trigonometric functions, some sines and cosines. Don't despair. You can check your answer with the graphing utility, or even better, look in the back of the workbook where we've given all the complete solutions. The analysis requires knowing about amplitude, periods, horizontal shifts, and vertical shifts. All right, what are we going to do next time? Well, we've only focused so far on the sine and cosine, haven't we? What do the other trigonometric functions look like? They're also functions. That's what we'll see next time, the graphs of the 4 remaining trigonometric functions. I'll see you then.